little bit more vector review before I jump into new stuff. Let's talk about dot products. So here's like by definition what a dot product is. If I have, let's say I have two vectors. I'm gonna draw a little x, yx, xy, whatever. Let's say I have two vectors A, and I have a second vector B. Okay, just two arbitrary vectors, and I can define. So I can say like A is, let's say it has components A1, A2, and then B we could say has components B1, B2. And then obviously if they're in the third dimension, they would have that third component, the Z component. The dot product is and remember, A1, A2, B1, B2, they're really just they're really scalars, right? Those are scalar quantities, because this is really the same thing as saying A1 times the vector I had plus A2 times the vector J had. So just remember, these are scalar quantities. The dot product, it looks like a multiplication symbol, and I'm multiplying them via dot product. It's an operation where you just take the components, multiply them, and then add them together. So what I'm doing for my x direction components, I multiply them. My y direction components, I multiply them, and then I add them together. That is literally just what a dot product is, by definition. Like, that is what we decided is a dot product. And then if there was a third dimension, you could do A3 times B3. I'm multiplying each like directional component, and then I'm adding them. X direction sum, or multiply. Y direction multiply. Z direction multiply. In the end, I add them together. Why is this useful, right? First of all, I talked about how A1, A2, those are really scalars. This right here is a scalar quantity. Like, this operation of the dot product outputs a scalar. When you're doing it with two vectors, it outputs a scalar. I guess when would you not be doing it with vectors? Now, why is this useful? This seems like a really stupid, and just for consistency, I'll make sure it's only these two, because those are my vector definitions. Why is this useful? Well, what I'm going to show you today by the end is that if you were to take the dot product of two vectors, it is the same thing as multiplying their magnitudes or lengths, their magnitudes, and times multiplying it by the cosine of the theta that they would form if you were to put their tails together. So you might be saying, well, what angle is being formed here? Remember, vectors are not defined by their starting point and ending point. You could put a vector anywhere and it's still the same vector as long as the magnitude and direction is the same. I could take this vector B and draw it from connecting the tail with the tail of A. And I know they don't look like the same vector because they're not parallel, but just roll with it. They're the same. So I could take their magnitudes, multiply them together with the cosine of that angle that they would form together, should I choose to draw them tail to tail. That's pretty cool, right? Like, that's pretty neat. Important things to note about this before I get into why this is true or show you how it's true. The dot product is kind of like measuring. It's almost like a way to measure how parallel two vectors are. Because, hey, if I draw, let's get some new vectors in here. Let's call them V and W. And if they are perpendicular with one another, right, then I know that V dot W, that's the vector name, right? That's just going to equal 0. I mean, cosine 90 degrees or cosine pi over 2 would always just end up equaling 0. So this dot product kind of tells me how parallel they are. Right now, they're not parallel at all. They're completely perpendicular. The dot product would equal 0. As I change that angle and make it more and more parallel with one another, then what you would get is eventually you would get cosine 0. right? Cosine 0, and that just ends up equaling 1. So 1 times straight up the lengths multiply, right? That's the maximum. Cosine 0, that's the max you get. Your max dot product possible is when they're completely parallel. So it's kind of like a measure of parallelness in a way. And you see that with work, right? It's the dot product of force times distance. The more parallel the two vectors are, the more work you get out for that given force and distance. So let's talk about where this comes from. First, I want to show you kind of a vector property, if you will. If you were to take, let's take A, right? If I were to do A dot A with itself, that is the same as doing, okay, well, A1, so remember this is vector A, A1, A2. So it's the same as doing, if I were to think about this operation right here, A1 times A1 plus A2 times A2. And that would end up equaling A1 squared plus A2 squared. And that is just the magnitude of A1 squared, right? Because if you think about Pythagorean theorem, the length of A1 is just equal to, or the length of A1 squared is just equal to A1 squared plus A2 squared. That seems intuitive, right? You're just doing A dot A. It's like you're kind of squaring it, but remember, vectors aren't scalars. You can't treat this like like scalars, right? This intuitive thing comes from like vector algebra. It's not like we're not using our normal rules where 3 squared equals 9 or 3 times 3 equals 3 squared. Like that's obviously true in the scalar world, but when you're dealing with vectors, you have to show that this relationship is true. That's why I did that. So let's talk about where does this come from. Where does this dot product thing come from? Let's zoom in on this A-B situation we got going on. So magnify. I don't want to draw it. I don't want to draw them too parallel. Let's draw it like this. Well, just pretend they're the same. I guess I'll draw it like here. Okay. So this angle's theta. Just for giggles, let's make a triangle. Why not? I want to make a triangle. I like triangles. So I'm going to draw in a length like so. Let's call this A. Let's call this B. And let's call this vector C. What is vector C? Well, vector C is just no, it's not. What is vector C? It is B. Yeah, it is B minus A. Because if I flip A and I draw A like so, if I do so this vector would be negative A, you could see that you would get C, and then this is like a parallelogram, and you can move that over. So just so that I like it when it's A minus B. So I'm gonna do A right here. But I didn't change anything. I'm just, oh wait, no, but I want to stay consistent. Okay, yeah, let's just roll with B minus A. Why not? I want to stay consistent to my definition that I have up here. So I had A here and B here. So this would be equal to B minus A. Well, let's use the law of cosines. Let's use the law of cosines to get somewhere with this. So the law of cosines tells us that the magnitude of C squared, so if I were to take the magnitude of C, square it, is going to equal the magnitude of A squared minus the magnitude of B. I'm drawing this wrong. It's a magnitude of A squared minus magnitude of B plus magnitude of B squared. Oh my goodness. Times 2 times the magnitudes times cosine theta. And I just ran out of space there. That's the law of cosines. If you're not too familiar with it, I would search up proof for that. Let's talk about, well, what is the magnitude of C squared? Well, I know vector C is the same as B minus A. So that would mean that the magnitudes are the same. right? Because it's literally the same vector, right? B minus A is a vector, so their magnitudes will be the same. And I know that, you could take magnitude of C squared will equal the same magnitude. And now you're saying, well, hey, I can just FOIL this out, right? I can do my binomial expansion, FOIL it out. But remember that, what was I going to say? Remember that we can't use scalar things that we've used like FOIL in the vector world. These are vectors. I don't know. Like I don't know if you could just FOIL it out. Really quickly though, I actually should, before I even get to the whole foiling thing, I do know that because of this relationship I showed here, I can say that C dot C is equal to C squared, right? I showed that here. A squared. I kind of got ahead of myself here. I forgot to show this part. My fault. And then therefore, if C is B minus A, I can say it's B minus A dot B minus A. Whoopsies. Kind of forgot to show that part. No big deal though. So yeah, if I'm trying to evaluate this, if I'm trying to evaluate like the left-hand side of this whole equation, right? If I'm trying to evaluate, well, what is, you can bring it over here now. What is B minus A dot itself? Well, first, you got to think about, well, what is the vector B minus A? Well, B minus A, if you think about B is this vector, A is this vector, B minus A is equal, B minus A is really just going to be A B1 minus A1 as the x component, and B2 minus A2 as the x component. So if I'm going to do this dot product right here, this dot product would end up equaling B1 minus A1, right, because that's the x component of this vector, times the x component of that vector, B1 minus A1, same thing, plus B2 minus A2, and then multiply it by B2 minus A2. And this is equal to B1 squared, and now these are scalars, so I can do my normal scalar binomial distribution stuff. Now, not binomial, expansion, sorry, not distribution. B1 squared minus 2A1 B1 plus A squared plus B2 squared minus 2A2 B2 plus A squared. Right, so I can do this, right? These are scalars. Now, all I really gotta do is what I'm really trying to show you here is, well, we have right here, we can use commutative property, B1 squared plus A1 squared. That's the same as the length of A. Oh, no, it's not. I'm so sorry. I'm completely doing the wrong thing. I don't know what I was thinking. A1 squared plus A2 squared. That's the same thing as the length of A1, or the A vector, right? A vector squared, its magnitude. So, same thing. B1 squared plus B2 squared. Well, that's just the magnitude of B squared. And then we're going to have minus 2 A1 B1 minus 2 A2 B2. Let's just factor out negative 2, because why not? Let me kneel down so I can write on the thing. We get A squared plus B squared minus 2 A1 B1 plus A2 B2. Well, hey, what's A1 B1 plus A2 B2? That's just the dot product right here, clear as day, of A dot B. So I could just write this as A dot B. So 2 times A dot B. So in other words, doing b minus a squared is kind of like foiling it out, right? I get b squared minus 2a dot b plus a squared. So I just showed that this operation of squaring the magnitude of the difference of two products is the same thing as doing just, not the same thing, but it's analogous to just doing a squared plus 2ab plus b squared, right? So that's pretty cool. What I can do now is just take this whole thing, move it back here, and hopefully, I don't even gotta really show the math. Look, a magnitude of a squared plus magnitude b squared minus 2ab. There is the same exact thing on each side. So I can really show that negative 2a dot b is equal to negative 2a b cosine theta. And then you can see the negatives should drop. And you get this. A dot b equals a b cosine theta. So there you go. You just use law of cosines and some things like here. Some things like here. You could use your vector properties in addition with your scalar properties and get this theorem. Hopefully that kind of made sense. You won't need to know this, but it's like, yeah, this is where the formula comes from. Let's talk about an application, or I guess applications of dot products in general. They're really good for computing lengths and angles, right? Let's say you're an architect and you made a room. I'll do this in red, because why not? Red is cool. It's a cool little thing. Cool little color. So let's say I made a room and it's cubical. Like I made a cube room. So how do you draw cubes? I guess like this, right? So I made a cubical room like so, and each edge length would be equal to A. So this is an A by A by A room. And let's say you take the diagonal of this cube, right? So you go from one corner to the opposite corner, like I did in my last example. And let's just try to draw this a little better so I can show you like what we're computing for, or what we're solving for. So that would be that vector. From corner to corner, we'll call it vector S. And, well, we're not really dealing with vectors. The main question is, what is the angle between the diagonal of the cube and the edge of the cube? So try to visualize that in 3D. You're taking that diagonal and finding the angle. Like, it would look like this. So if I draw my... let's just do this in blue. I realize my red is really crummy. It would look like if I were to just draw my ZYX, it would look like finding that angle right there. Like it's kind of hard to visualize. You could just search up like angle, well, you'll get the answer, but I'm gonna show the answer. You can just search up diagonal of a cube, the angle between the diagonal of a cube and an edge of the cube. Hopefully that'll show like a good like idea, or hopefully you can just imagine that. Let's think about how can we use the dot product to do that? Well, let's think about vector S. If this is the X and this is the Y and this is the Z, then I know my vector S has components A, right? It's a cube. So it would, from corner to the opposite corner, it would be A. Hopefully that kind of, whoa, that was a good way to show it. You're going A. That's how you get to the other corner. And then let's say we have another vector L that is just that's just the edge. That would equal just A, 0, 0, right? Because it's only in the X direction. Let's try to find the angle between these two vectors. Well, we just do a dot product. And then we can multiply their lengths and then find what that cosine theta would be. So the dot product, so let's just write this out. What we're doing S dot L, which would equal magnitude S times magnitude L cosine theta. And S dot L would be the same thing, right? We're multiplying x components and then adding it with the multiplication of the y and then the multiplication of the z. So it would be the same thing as a times a plus a times 0 plus a times 0. And these just end up being 0, so you end up just getting a squared. So a squared would be equal to, now what's the magnitude of s? In our last video we showed, or my last video, I showed that it would end up equaling a squared plus a squared plus a squared. Like it would end up equaling the square root of the sum of the squares of each component. Times, now what's the magnitude of L? Well, it's just in one direction, it's a, right? It's just, that's literally the length of the edge, a. Cosine theta, that's what we're solving for. So I can drop one of these a's and I get a, right? Just a equals this. So I really get a over square root 3a squared equals cosine theta. Right, this would be the same as a root 3. So I really get cosine theta would equal 1 over root 3. And hey, I can use inverse trig to solve for what that angle is. It would end up being, I think, 54.7 degrees, and you can Google that. That is literally like a true thing, right? The angle between the diagonal and the edge. So that's one use case of dot products. I'll be making more videos on determinants and other stuff. I'm really mirroring, I'm watching the MIT OpenCourseWare for Calc 3, so I'm just kind of mirroring that, but also explaining it differently, hopefully. And yeah, hopefully this was kind of helpful. I don't know. Hopefully you can go out and use dot products now in your long weekend.